Hello, good morning. I'm Dr. Shobha, Professor of Computer Science and Engineering Department, RV College of Engineering, Bangalore. Today, I'll be talking on the implementation of generative adversarial networks in HPCC Systems platform. Already you must be knowing why generative adversarial networks, I'll call it as GAN here, is an important thing for generating the data for which will be useful for big data analytics. And this will be generated on HPCC Systems platform, which will be more useful for distributed computing. So my agenda goes like this. We have first, I will just talk about what is this HPCC Systems platform, Generative Adversarial Network, Generalized Neural Network Bundle, GAN on HPCC Systems platform, results, conclusions, and references. So HPCC Systems platform is an open source distributed computing system. So the main architecture of this is, as you can see from the figure, you have a big data which comprises of unstructured, semi-structured, or or structured data. So when this is got to this particular platform, you have two clusters, built-in two clusters, that is Tor and Roxy, mainly used for computation and distributed computing. Tor takes care of extraction, transformation, and loading. It is an ETL tool. And similarly, Roxy, it is mainly used for delivering the solutions to the queries raised by the users. And these things are developed by making use of ECL, that is Enterprise Control Language, which is a parallel declarative language. So as I told, ECL is a declarative language and it follows data flow architecture for managing the data flow in high performance computing cluster, that is HPCC, while preserving the cluster computing which was developed using C++. ECL is mainly a powerful language for big data processing and computations. It follows data flow architecture in context of ECL programs and which flows the data from one activity to the other activity. So you can see here, this is the data flow architecture. This is the SIPnet of the ECL code. Here what I am doing is, I am reading a data set which has an employee, first name and last name, and you have a salary. This data set. So these two data sets are merged together. So you can see here join employee and salary, and or joining get employee salary. We are merging with respect to the left ID is equal to right ID. That is the employee ID. So data flow architecture, how it does this, you can see the graph here. Since we are taking an inline data set here, it shows the data flow. Okay, usually what we do is we have a program and we have a data fed into it. But here the data will flow, that is the program will flow where the data is. Okay, so that is a declarative and data flow architecture. You can see here inline data set, we are joining here and this is the output. So the data flows from one activity to the other activity. Okay, so this is about the data flow architecture. Then we will take up with GAN. What is this generative adversarial networks? So as you can see from the figure, we have a customer and we have a shop owner. Customer gives the wine, sells the wine to the shop owner, and shop owner buys it. Okay, thinking that it is a real wine, and he buys it. But a forger may also sell a wine, which may be a fake wine, to the shop owner. But the shop owner should be able to distinguish between the real wine and the fake wine. Okay, So this is nothing but a discriminator. The shop owner is nothing but a discriminator who discriminates the real and the fake wine. So in the computation thing, we have, say, the noise vector. Noise vector means a forger's inspiration. That is, he is going to sell the fake wine. Then a generator. Generator is, in this case, it is a forger. Okay, we will generate a fake data. That is a fake wine. Okay, and this fake wine is sold to the shop owner. The shop owner should know. Okay, he should have a capability to decide whether it is a authentic wine or not. Okay, so based upon whether it is authenticated or a fake, he will classify it. Okay, so the whole thing, whole concept is taken care by generative adversarial networks. It has two network. It generates the data and the find out whatever the data that is generated, is it a real data or the fake data. Okay. These are the things. So as I told you, generative adversarial network is a pair of models. It behaves as adversaries to each other in order to compete and learn from experience and generate artificial data similar to the data given to the model for training. So you can see here the real world images, and whatever the sample we get from real world images are real data. Okay, that is fed to the discriminator. A generator, it takes the thing from the latent trained random variable and generates the sample. So the discriminator will have the sample from the real world image and the sample from the generated image. And this discriminator should identify whether it is a real image or a fake image. If it is a fake image, what is the loss? That is, how it is different from the real image, that it has to find out, and that we call it as a loss here. And this loss should again be given to the generator, sorry, to the discriminator, and discriminator again, okay, it decides on what sample should be generated, okay, and it creates the image. And that image again, we have to see whether it is matching with the real image. If not, what is the loss? Again, if there is a loss, again feed it to the discriminator until we get the real image. That is what here it is given in the description. The generative network keeps producing the image that are closer in appearance to the real images, while the discriminative network is trying to determine the difference between the real and the fake image. So the ultimate goal is to have a generative network that can produce the image which are indistinguishable from the real ones. This is the functionality of the GAN. So this GAN is implemented on HPCC Systems platform, which is a high performance computing cluster, which is an open source, and it provides a distributed environment so that the images whatever is generated will take less amount of time. So this HPCC Systems, which is in the distributed environment, it is implemented by using Generalized Neural Network Bundle, that we call it as GNN Bundle. So this functionality is already there in the HPCC Systems platform. But we are providing more features on this GAN bundle. So already, what are the GAN features we have on HPCC, we'll see, and what features we are going to add on, that also we will look into it. Generalized Neural Network Bundle is a bundle which is already existing, and it provides a generalized ECL interface to Keras. It is similar to the TensorFlow in Python 3.6. The only difference is ECL is mainly used for distributed computing. That parallelly, the computations will go on. Okay, and all the functionality, whatever the TensorFlow provides in Python, ECL interface to Keras also provides. It has various functions, just like TensorFlow. It has various functions for the development and usage of neural networks, and it is very similar to Keras. So GNN Bundle, it utilizes HPCC Systems multi-node processing capability by treating each node on the cluster as a thread. This fills the gap between ECL and Python. But this is suitable for sequential Keras, and it is unsuitable for Keras functional model. Existing GNN bundle, it contains two modules. One is GNNI, that is Generalized Neural Network Interface module, and the TensorFlow module. What this GNNI module does is, it creates a session, that is, it creates a TensorFlow session which share global variables for a set of neural network models. It defines the model, that is sequential Keras model, given the session ID, definition of each layer as a list of strings, and compile definition as a string. It fits the data into the model and also predicts the data using the model according to the input data. Finally, it has a weight transfer technology. It retrieves the weight from the model and stores the weight to the JSON files and evaluates the model. Once I build the model, the evaluation metrics are also there in GNN bundle, which can be used to evaluate the model that has been present. Then the second one is tensor module, which is similar to NumPy in Python 3.6 for inputting the data, keeping track of data as an n-dimensional array, and provided as a tensor for handling the input data. The same concept is there in the ECL also. ECL, it has tensor, which is a record structure. It stores more information than the n-dimensional array and also convert the input data to TensorFlow. Some of the features that is included in the TensorFlow module are building tensors. Okay, that is t.tensor dataset is built using defined function in this model, aligning tensors to n-dimensional mismatch, and get the data from the tensor, and some of the miscellaneous features to reshape the tensors, add multiple tensor element wise, and get the number of records onto a tensor. These are all the features which is already existing in HPCC systems. But the major drawback is these features are adequate to numerical record. It requires more processing when we have images. Okay, when this GAN is applied to images. So these limitations has to be overcome. So in order to see what are the limitations the image module has is, processing an image to give as input to the neural network developed in GNN is a difficult job due to ECL being a structured language. Okay, till now, whatever is present in the GAN bundle, it takes care of numerical processing. But if I go for an image, since ECL is a structured language, giving an input to the neural networks finds it difficult. Defining a structure was required with converting a compressed image format like JPEG into a matrix numbers and transform the dataset to a specific structure in order to make the tensors. So taking this drawback of the image, some of the features were implemented in the image module. That means we have contributed to the GNN bundle. Okay. So we have taken MNIST dataset, which are the functions that are implemented to input the image and labels of both train and test dataset. So the input image can be of any format, but it is taken as a stream of bytes and is converted into n-dimensional array as just as Python using OpenCV2 functions. And the matrix, whatever we get, is flattened and returned along with the dimension as a dataset in ECL. It ensures that all the images are of the same format. This is the input. So image is given to the sensors. The image, which is an unsigned integer, is converted into the tensor as required by the neural network in GNN to take the input image. Tensor to image, T tensor given from the neural network as output was converted back to an image for output in several ways. Similarly, the output image, whatever we get from the neural network, is a set of numbers and it was converted into NumPy matrix and encoded into an image in JPG, PNG or BMP format for seeing the output. Now, this features was implemented on GAN for HPCC systems. It had input phase. So, input of data given to the GAN needs to be processed to suit the needs of the GNN bundle. Training data was performed into the dataset defined by dense data, and this dense data has a record structure with indexes and values. Okay, so indexes and values mainly gives you the position of the pixel in the input. What is the position of the pixel in the input of the matrix? Dense data simulates the representation of an n-dimensional array in NumPy module with the indexes and values together to represent the position of an array. All the data required to be used need to be transformed into a structure of dense data that is used by making use of various transformation operations that are there in ECL. Next, we have to define the models. Here we require two models, that is generator and the discriminator, which act as adversaries to each other. And these models are required to be given by the user. User decides on the generative and discriminator model definitions and adds the definition in each layer into a set of strings. So generator and discriminator are defined using these functions, that is GNN function defined model. A combined model, which is the generator stacked over the discriminator, needs to be defined. Next, after we generate the image, next is the training phase. Each epoch of GAN training happens in this way. It generates the data from random latent variable using the generator, fits the data with the label 1 to discriminator, and it fits the generated data with label 0 to discriminator, fit the random latent variable with label 1 to the combined model, since discriminator is non-trainable. Generator is trained with a random latent variable while fitting as per the discriminator ways. In Keras API of Python 3.6, okay, it is already a built-in combined model is there. By adding the generator and the discriminator as object, which link their layer weights. Okay, layer weights is whatever we have seen in the Python. Okay, same the weight transfer technology is already available, but in ECL we have to manually transfer the weights. For this weight transfer mechanism, we have implemented getWeight setWeight function in GNN bundle of GNN bundle. GNN model of GNN bundle. So this is the weight transfer methodology. You can see here that you have a combined weights. Okay, that is the modified weights, because the discriminator will know the fake and the real image and finds the loss. Based upon this loss, the weights will be modified from the discriminator, and the modified weight should be transferred to the combined model. For efficient fitting of the data to the discriminator is effective in the epoch. Trained weights of the combined model need to be given to the generator to predict the noise. So this goes on. You can see here, generator, it predicts from the noise, but the discriminator, it fits the real data. Okay, and it also, the generator also will be taken care as an input to the generated data. So you have trained discriminator weights here, and the merge weights, again it will be the combined weights. Again the process will be repeated until the fake images matches with the real image. So This is done by means of weight transfer methodology. For experimental result, as we told, the dataset is what? MNIST dataset. There are two architectures of the GAN which we have used to check whether the implemented features for the image is working properly or not. The architectures that were used is simple dense layer based GAN and deep convolution GAN. Okay, in simple dense layer GAN, okay, dense space network, it is a dense space network with no special transformation except we have batch normalization, dropout and activation layers. And it allows the GAN to be trained pixel wise. Training is very slow here. So the generated image are not so smooth. As you can see, the generated image, you can see here the numbers which we have generated, it is not so smooth in simple dense layer network. Then we have one more model. It is deep convolution GAN, which makes use of multiple convolution layers. It helps the model in recognizing various features of the image. Since there are n number of convolution network, you can see the image in each epoch 2000. As we increase, the numbers whatever we have that has been generated by the GAN is more smooth. Okay, this is coming to the conclusion. We successfully implemented on HPCC systems to be able to execute any KRAS sequential GAN, and it has been tested and found stable for the models on this HPCC system platform. These are all the references, and thank you for giving me an opportunity to speak here, and any feedback you can write to me during the conference. Thank you.